Hi, my name is Simon Crosby. I'm going to talk to you today about delivering continuous intelligence from stream data and from lots of data and lots of data sources. In particular, if you just look at this last year, ARM themselves licensed over 20 billion CPU cores. That's about 2 million an hour. And every one of them, you can bet, has a lot to say. So we're moving rapidly into a situation where every product is instrumented, everything has a lot to say, and it all has clues which need to be analyzed. How do we get insights into that fast? Let me give you another couple of examples. If we want to make a smart city, the city of Palo Alto and its few hundred traffic lights deliver more data per day than all of Twitter. And Las Vegas, about 10 times the amount of information in the Library of Congress every single day. Now, these are vast amounts of information. I'm going to show you an application which uses even more data than that. In fact, this application uses as much information as Facebook has to process in a single day. So what is it? Well, we're processing streaming data from every single base station in a mobile network belonging to a carrier to continually optimize connection quality for mobile devices, more than 100 million mobile devices, and tens of thousands of base stations to enable them to continuously assign network capacity in the best way to each one of the devices to maximize connection quality for all their users. Now, this can also be used in a very interesting way to find devices where connections have failed, or to find base stations where connection quality is poor or has failed the users, and to reassign capacity. Now, to be able to process 4 petabytes of information per day in real time imposes a massive complication on the infrastructure. But what I want to point out here is that most importantly, storing information for later analysis doesn't cut it for a bunch of reasons. First of all, data value is short-lived. There's no point in trying to find a better connection for you tomorrow if the problem is that your device is not connected right now. But more importantly, the flows of information are boundless. So this just is out of sync with this idea of store and analyze. There is so much information, you couldn't afford to store it. It's very expensive to do so, and the infrastructure required is huge. So in this case, the customer was using more than 400 nodes of Hadoop and is moving to only 40 nodes of Swim. And that's really because we can give them all of the benefits of Moore's law back by adopting an architecture which is stateful and gives them Moore's law benefits by keeping everything in memory. Store and analyze is slow by comparison, and it's really just mismatched with the evolving need, or at least the new enterprise reality, which is that instantaneous understanding of the environment is key. So if you take away one thing from this presentation, take away this. Store and analyze was a great idea when Google was started, and when the Hadoop folks first escaped from Google and Yahoo, but it's no longer appropriate. Nowadays, what we need to do is to analyze data on the fly, react immediately, and then if we really care about it, or if we really need it, we'll store the data later. But disks go slowly relative to CPUs, as we'll see. But there's more to it than this. Applications that deliver continuous intelligence need to always have the answer. And you can think of tons of safety critical or other applications that rely on edge data, where we need the answer immediately. We can't afford to store things on disk and analyze it later. So we have to analyze, learn, and predict on the fly on the basis of streaming data without going to a disk, putting information in a database or some other form of storage. So here in particular, data drives computation. When data shows up, we compute nuances. And of course, that inverts the control loop of many applications where traditionally a UI or a user query or something drove the application to go and query a database. So what's the consequence of an architecture like this? In Palo Alto, I can publish via streaming API predictions for the forward-looking 2 minutes of every intersection as to what it's going to do. And that API can be consumed by folks like Uber to better route their vehicles through a city infrastructure to minimize journey times, okay? So this notion of computing on data as it arrives to analyze it and predict on the fly is critical. And storing the data is really irrelevant. You really don't care that a light was green last Tuesday at 8:07 a.m. Let me give you another example, just because it's computationally fierce, from traffic work we've done in Dubai. Here is an interesting query. Find trucks that are in or approaching a banned area. Maybe there's a festival going on. Okay, so the notion here is that we have to continuously reevaluate every truck for every GPS update relative to a geofence, which is the banned area. Or perhaps, as I show at the bottom here, find trucks with bad braking behavior, which is a sequence of GPS updates, and then alert the nearest inspector. And every one of these requires, every single update, a bunch of reevaluations and potential reactions. Okay, very hard to do in traditional database world. All right, if we can adopt an approach like this, a stateful approach, then we can get answers 1,000,000 times faster. And by the way, this is very little more than giving you the full benefit of Moore's law, as you're about to see. So this is about stateful architecture, keeping data and state in memory and analyzing on the fly. You get to use a ton less infrastructure as a result because you aren't storing everything on disk someplace and having to get it back. So you end up with less infrastructure. In the case of the mobile carrier that I was telling you about, they moved from 400 nodes of Hadoop down to about 40 nodes of Swim. And that's pretty awesome. Applications in this world are easy to develop and operate. So people think of it as a radically different paradigm. It isn't. It's just the actor model, which is a simple extension of what you already know in the React frameworks that are becoming popular. And if we can adopt a model like this, then data, or at least state of everything, is in memory. And so we can go and do data science on live things, live representations of things in memory, and even deploy new analytical algorithms on the fly. So it's a pretty cool approach. Now, my analogy for 1,000,000 times faster is precisely this. If a CPU can execute an instruction about a nanosecond, let's call that the speed of an F-18. It turns out that a snail is about 1,000,000 times slower, okay? That's about the same as reading 1 megabyte from disk, okay? Or maybe the same as pinging US West to US East. So whether or not your data is locally stored in a local database, or whether it's across a network or in some other store, the moment you hit some peripheral notion of a network or a disk, you're going way slowly. And this concept of 1,000,000 times slower is really crucial because it leads to very substantially greater costs and very much increased end-to-end latency per event. Okay, another way to think of that is that if you think of stateless computing, which is the cloud, and databases, which is where you keep all your state, really what they've done is given you the ability to deal with huge throughput by going wide, but they don't grow in terms of giving you the advantage of Moore's law, which are really primarily CPU and memory based, by growing up. Okay, so by contrast, a stateful computing model scales both up and out. I'll explain how in the context of SWIM, and it gives us this amazing performance benefit. Instead of going to storage, we're going to drive computation from data directly. And so we get to invert the control loops. So instead of UIs or queries driving polls of applications to go and query databases, we get to compute whenever data arrives. And whenever data arrives, we get to use real world context to find meaning. And in particular, analysis of a single event stream may be kind of cool, but it doesn't really tell you things like correlation or related to, or let you predict based on environmental circumstances. We need to make all this stuff easy for normal humans. And so a key requirement here is we want to use languages and ops tools that everybody knows already. In my case, Java and Python. So how do we do this? The open source project I'm going to use here is called swimos. I want you to think of it as being a bit like LinkedIn for things. So what does Swim do? It creates a stateful concurrent actor, think of it as an actor, which is a web agent. Why we call it a web agent? Because its object ID is a URI for every single data source. Okay, and this continuously and statefully analyzes data from its real-world sibling. So you can think of these as objects, but concurrent objects that are continuously evaluating their own real-world state. Cool beans. That's only step one, though. Each one of these web agents continuously and dynamically links to related web agents. And this notion of relation is, you know, anything. It could be as simple things like trucks have engines, which is well known from the relational model, but it can also be computational, which gives us this fluidity. So for example, correlated to or predicted to be within, or geofenced, okay? And so what we're doing here is building an in-memory graph, which links these web agents based on the situation they're in. And now we're going to look across all of their data to make sense of it. So we're building a big in-memory graph, a bit like LinkedIn, which is fluid and links these web agents, and they can use not only their own state, but also the state of their neighborhood, whatever they're linked to continuously analyze, learn, and predict. And then they stream their own insights, their results of their computations to UIs, to storage, to other applications in real time. And when I say real time, everything operates in sync with the real world as fast as Moore's law will let us go. So let's give you a couple of examples. Things that web agents can do. They can learn and predict. I'm going to dig into this as a good example in the next slide. Using new data as the learn and predict to predict their own future. They can respond to queries. So for example, deep MapReduce type queries. They can compute over graphs, over the graph they have built, and relational queries, which I think of as very simplistic in a sense. So KSQL being an example from the Kafka world. They can perform analysis, and there are a bunch of really interesting algorithms here, which are better known as sketches or statistical data structures, which we use to learn over boundless data. And of course, these web agents, because they're programmatic, can integrate with any other pieces of your infrastructure, apps written in Spark or Flink. But more importantly, you can wire them up directly to something like Jupyter and go at them to do live data science. Let's give an example of the learn and predict type behavior. Web agents can compute on time basis or whenever data arrives. Here, in my traffic example, every kind of digital twin of an intersection is periodically going to form an input vector from its own state plus the state of its neighbors and throw that through a DNN. And on day one, the weights of the DNN links are all random. And so what pops out is a guess. And we then have the opportunity to compare that with the real world and take the difference and backpropagate. So every single time this thing runs, we get an error which we can backpropagate, and we can watch this error to make sure that it converges. And over time, these weights converge, hopefully, on a stable amount, a stable predictive capability, and we'll see this predictor becoming stable. Now, these are small DNNs. Most importantly, they're not trained in the cloud with historical data by data scientists. They train themselves, and so the same code that runs in Palo Alto will run in Houston. We don't have to have a per situation model. It's very, very powerful. And an application then is an active graph, a graph of these web agents. Now, just building a graph of web agents is kind of ho-hum. What's important here is that they are dynamically related to one another by some real-world constraints. So, for example, this digital twin of an intersection is going to link to every other of its neighbors, everything within 1,000 meters, okay? And when it analyzes and learns and predicts, it will use its own data and the data of its neighbors to do so. So the application is a set of independent computational graphs, each of which is all hooked up together to make the application for a city. Notice that the application programmer only has to describe a single intersection, which is composed of a bunch of lights and sensors and how they interact and their relationship to logical neighbors. The arriving data builds the application and scales it in memory. And so again, tiny bit of code, 2 megabytes of code runs great in Palo Alto and will scale to the size of Houston, building an in-memory model. Okay, where does this stuff run? Well, this is a very important question and worthy of follow-up discussion. So reach out to me if you want to know more. But the one thing I want to point out is that edge compute is mostly a nonsense concept. Edge compute does not take into account that the edge really isn't a place. We compute whenever we get our fingers on the bits. And so the edge is where your data comes from. And you compute whenever you can, that is as close to where the data originates to reduce volume of data and to minimize response time. But often that's in the cloud. So I don't like a distinction between edge and cloud computing specifically. You compute wherever you can. And so typically swim applications are deployed using something like Kubernetes, and we're deploying containers on top of Linux. Each swim instance is just a container which contains, I guess, roughly 3 layers, a runtime layer, which is going to ensure that these instances can communicate, that web agents can stably compute across a distributed cluster. The machinery for making the model, so this digital twin model, I guess, and then streaming analysis and learning algorithms, which are going to use to process streaming data. And so a swim application is deployed as a set of instances. The instances interconnect using WebSockets. And then at the application layer, swim moves around web agents on the fly to maximize their performance and minimize total costs. So for example, the web agents which are filtering out raw data and getting down to state, so going from voltage swings down to green or red, move to the physical edge, and those which are doing analysis move to places which are more suited for analysis. Lots of memory, big CPUs, GPUs, and so on, perhaps GPU-attached instances in the cloud. But Swim really doesn't care at this layer. It's going to optimize for that constraint. And so if you happen to have local compute resources which met the requirement, then Swim would just use them. Okay, so Swim really does solve an application layer issue of where things should run dynamically based on cost and performance, and not an infrastructural level. Right, I'm going to summarize here. Continuous intelligence applications are those which analyze, learn, and predict on the fly. It's an emerging category, but it's vital. Watch this space. These are applications which always have the answer because they have to. If you're going to meet their customers' needs, you have to be able to tell them what's going on with their infrastructure right away. They can react in real time because they're basically programs, and their programs composed of lots and lots, perhaps billions of these little web agents. If you approach the problem in a stateful way by keeping state in memory and throwing away raw data, you get to go 1,000,000 times faster. And I just want to remind you of that. That's about the same as a Snell versus an F-18. And that is an unbelievable performance gain for many applications. You also get to reduce the amount of infrastructure you need by about 90%, which is absolutely phenomenal. You can develop and run applications using tools you already know. So it's kind of the reactive paradigm. And we use Java applications, and Swim is simply a set of extensions to Java. And you can then do data science on live data, effectively changing your analytical algorithms on the fly to suit your current needs. Okay, I'll stop here. Thank you very much.